Hi, welcome to this series of 5 lectures on the principles of flight. These are all geared to get you up to a standard of knowledge so you can pass the principles of flight exam for the sailplane pilot's license. In this section, we're going to talk about the wing section, how forces are represented in aeronautical explanations, how those forces are resolved and how we end up therefore with lift and drag, the Venturi effect as part of how a wing works, the lift distribution, how that's distributed around a wing, and the coefficient of lift. So first of all, it's important to understand that wing sections have changed over years as our knowledge has developed. And you can see on this screen here, we've got an early picture of an early low speed, high lift wing sailplane back in the 30s and 40s. These were designed, and then below it we've got a wing section of a modern high performance sailplane. And over the years we've gathered more and more understanding of how these things work, and then applied that to the design of aircraft, along with new materials, new composites, which have made it possible to build stronger, lighter structures. So first of all, what I'd like you to understand is how the diagrams that you look at are presented to you. You normally see pictures of wings or aerofoils with the air flowing around them as if they were in a wind tunnel or something like that, as a way of explaining what's happening to the airflow around the wing. In reality, however, it's the wing which is moving and it's the air that is stationary. And this is quite an important thing just to bear in mind, because although the drawings in books and so forth are very helpful, they can sometimes lead to a bit of confusion. So just remember the wing is the thing that's moving and the air is the thing that's stationary. So if we place a flat plate into the airflow, the airflow is deflected downwards, and this reaction is what we would feel if, for instance, we were driving down the road and put our hand outside of the window of a car and inclined our hand into the airflow. We'd feel a force wanting to push our hand up and back at the same time as your hand is deflecting the air downwards. Now, the angle between this relative airflow, as it's called, and the plate is called the angle of attack. And as you can see in this diagram, it's relatively easy to understand and relatively easy to measure. However, when we're talking about an aerofoil or a wing, the surface is curved. Now, this isn't quite so easy now to measure the angle between that and the relative airflow. And for this reason, we create a datum line. This line we call the chord, and the chord is a straight line drawn between the leading edge and the trailing edge of the wing. It's actually the point of maximum curvature on the leading edge to the point of maximum curvature on the trailing edge. The angle between that and the relative airflow is the angle of attack. And because the wing itself is disturbing the airflow immediately around it, we make this measurement with the relative airflow some distance away from the airflow itself. When we represent forces in diagrams, of course, if you think back to the flat plate for a moment, we have a pressure upwards on the plate, and we could represent that as a series of little arrows, as I've drawn on here. And let's suppose that's 10 square feet of wing area, and each square foot is being driven upwards by a force of £2, so £2 per square feet, then it might be more convenient to draw this all as one force, and we would call that the total aerodynamic reaction or total reaction, and we could represent that just by one single arrow. Now, the point that this force acts on the wing is called the center of pressure. This is an important thing just to remember. So far, we've got some terms that we need to just get used to. The first one is relative airflow. So that's the airflow in relation to the wing itself. Second is the angle of attack, so the angle between the chord and the relative airflow. The third is the center of pressure, and that's the point at which we can assume that the lifting force or the total reaction is being applied, and then the chord. And we haven't shown the chord in this diagram just yet. It's also important to realize when we're looking at this that it's all relative. So you notice that the airflow isn't horizontal. It's actually, in this diagram, shown as an angle. The wing works irrespective of the attitude in relation to the horizon. So it's about relative movement. So the direction of travel is the key thing. Now, just a little bit about the resolution of forces. Forces can be shown on diagrams like this as vectors, and you may not be used to the idea of a vector, so a quick explanation here might help you. If you look at the diagram here on the left, we can see an object moving towards the Earth, and there's a force acting on that. It's been dropped. It's called weight. And the force is the result of gravity, so the attraction to the Earth's surface. So that force is being shown by a red arrow underneath pointing downwards. Now, resisting that weight falling is air resistance. So a certain amount of restriction in its movement is created by it having to move through the air. And you can see that the air resistance is marked by an arrow pointing vertically upwards, and that's a smaller arrow because the force is smaller. So these vectors, the length of the arrow represents the magnitude of the force, and the direction of the arrow represents the direction it's actually moving. So if I just move on to the next slide, a body that's being affected by forces on it can have more than one force acting on it. And when that happens, we can resolve that or those forces into one resultant force. So we've got things pulling it in two directions, and we can create a little diagram to work out exactly where that object's going to move. So if you look at the top diagram, here on the left, you can see that the object is being pulled in two exactly opposite directions by two exactly equal forces, and the net result is it doesn't move. So the resultant is zero. In fact, in this case, there's no movement. Now, as you go back down to the lower diagrams, you can see that we have now introduced force 1 and force 2. And these two forces are pulling on the object, and the object will then move as a result of those two forces. It won't move directly towards F1 or directly towards F2. It'll move somewhere in between the two. And if we draw a parallelogram around that, we can put F1 in, the length of the arrow representing the strength of the force, and the direction of the arrow represents the direction of the force, and equally for F2. And if we create a parallelogram, then the diagonal on that, which we've marked R, will show the resultant direction that that object will move. So we can therefore use this idea of a parallelogram of forces in order to find the resultant force. Now, this idea can be worked back the other way. So we can have one force and split it into two convenient forces. And this is often done. And in aviation, it's done a lot. So in this particular set here, if you look at the upper diagram, you can see the force F has been split into two resultant forces, if you like, R1 and R2. They are replacement forces. And if to create this, the original force is exactly whatever it was, and we then construct around it two equivalent forces that would, if they acted on the body in that way, would end up with the result of the movement that you see. So we can select virtually any direction we like. And in the case of a wing, if we go back to our flat plate and our total aerodynamic reaction, what we can do is split this total aerodynamic reaction, or TR, into two vectors. And we'll call one of them lift, marked L on here, and the other one drag. So they're just introduced for convenience for the engineer to understand and unravel what's happening with the wing. And in this example, and in all aerodynamic examples, lift is placed as 90 degrees to the direction of travel of the wing. And drag is parallel with that force and in the opposite direction. So we can now create a parallelogram of forces L and D and lift and drag as a purely arbitrary thing, and that's where they originate. And lift is effectively 90 degrees to the relative airflow, and drag is parallel to the relative airflow. So we could summarize that as saying that lift, when we talk about lift, it's part of the total reaction, acting at right angles to the free airflow. And drag is part of that total reaction, acting parallel to the free airflow. And the better the lift-drag ratio, the more efficient the wing is. So we'll very often hear glider pilots talking about best LDs and stuff like that. And they're really talking about this lift-drag ratio. So if we now try to understand a little bit about how the wing itself works. And so for that purpose, I've given you two diagrams here. One is an aerofoil in with some streamlines of air moving around it, and underneath we have a venturi. In the case of the flat plate we were looking at, we were simply considering the effect on the lower surface. But now I'd like to consider the airflow around the whole wing section. The path of the air travelling over the upper surface is not the same as the path of the air travelling on the undersurface. And like the venturi, if you look at the venturi, you can see that air is funneled. It's going through a wide mouth, if you like, and then being forced into a narrow channel. And for it to get through, it needs to accelerate. And it's this acceleration which is the important factor. So the air moves in, accelerates as it goes past the restriction and comes out the other side. And this venturi effect has the effect of reducing the pressure in that tube. And the same thing happens with a wing. The airflow traveling across the top of the wing is accelerated, and this in turn reduces the pressure on the upper surface of the wing. So The air, therefore, passing through the venturi, accelerates, and the pressure at the narrowest part of that is therefore reduced. And this takes us into Bernoulli's theorem. Bernoulli developed this in the 1700s, and I don't want to bog you down with lots of physics, but fundamentally, the energy due to pressure as a plus the energy due to velocity remains a constant. So you increase one, you reduce the other, and that's fundamentally Bernoulli's principle. So with increased velocity, there is a reduction in static pressure, and with this with decreased velocity, there's increased static pressure. What this leads to is a rather stunning result. And that is 2/3 of the lift that a wing generates is created by the upper surface of the wing. And only about a third, approximately a third, is created from underneath. And it's this difference in pressure from top to bottom of the wing which is making the wing work. And the actual pressure differences here are quite small. So if you can see here the figures, if the atmospheric pressure was 211.7 pounds per square feet, the pressure above the wing is lower by about 4 pounds per square foot. So a tiny, tiny, tiny relative amount. And then underneath the pressure is about 2 pounds per square foot greater. So they're very small, which is why gliders benefit from having larger wings. Now we can move forward and look at the coefficient of lift, or the lift coefficient. And there is a correlation between the angle of attack, so the measured angle between the relative airflow and the chord of the wing, and the amount of lift that's generated. If we increase this angle of attack, we increase the amount of lift that the wing generates. And this diagram is showing it. So you can see that by the time we get to 10 degrees angle of attack, the coefficient of lift is relatively high. The amount of lift being generated is fairly high. But when we get to about 15 or 16 degrees, it starts to sharply tail off. And the reason for this is the airflow is now no longer laminar. It's no longer sticking to the wing properly because the angle's too great. And so this suction effect is lost. And that's the stall, effectively. So we can adjust the speed of a glider by changing the angle of attack, and we can also adjust the amount of lift generated by changing the angle of attack. And just a little point on this diagram, if you look right down at the bottom, it says in unaccelerated flight, and that simply means it's at 1G. The aircraft is in steady flight. If we're accelerating or decelerating, then it will change the results. Now, other factors which affect lift are the speed of the aircraft or the wing as it's traveling through the air, the density of the air, so the denser the air, the greater the lift it will produce, and the size of the wing, or the square area. Now, the increasing the square area of the wing will increase the lift, but of course there's not much a pilot can do normally to change the size of the wing. We increasing the air density will increase the lift generated, and what that means is gliders or any aircraft will be more efficient. It will take off more readily. It needs a shorter ground run than if it's in a low density air mass. And if we increase the velocity, so the speed that the wing is traveling through the air, then we will increase the amount of lift that it's generating. And we change this velocity by changing the angle of attack. This is the key thing. So if I now take you back to the coefficient of lift diagram, we can see that at high speed we have a relatively small angle of attack and a relatively small contribution to the total lift. And at low speed we have a higher angle of attack, and therefore it provides a greater contribution to the lift being created by the wing. And you've no need to memorize this or anything, but it is a very elegant little formula, and you'll come across it often. So notice here the total lift equals the coefficient of lift, which is directly related to angle of attack, half rho, and rho is the Greek symbol used for air density, v squared, which is the velocity squared times the square area of the wing. And the two things that a pilot can affect are CL and v squared. And so if we fly faster, we use a smaller angle of attack. If we decrease speed, we have a higher angle of attack. And CL and V squared basically balance each other out. And this is what you're doing, for instance, when you're landing your glider. You're progressively increasing the angle of attack as the aircraft decelerates during the hold off to land. So now, just in summary, what we've looked at is the wing sections, broadly how they've developed, how forces are represented in aerodynamic drawings, how those forces are resolved, how we've arrived at lift and drag, the Venturi effect, lift distribution, and the lift coefficient. Now, there's some questions in the following section, and if you find difficulty in answering them, can I suggest that you just run back through this tutorial to get yourself the answers so you're comfortable with it. Thank you very much, and I'll speak to you next time.